In this session, I'll give a live demonstration on external incompressible CFD analysis of Wing by using SimScale software. SimScale software is a cloud software. To access SimScale software, open browser or Microsoft Edge and enter the web address simscale.com. Next, go to Dashboard, create new project, give the project title. I'll give it as Aircraft Wing. Describe your project. I'll describe it as external incompressible CFD analysis. Choose category as aerospace and click on create project. The first step in analysis is import geometry. To import geometry, click on the plus icon in geometry, import from computer, select your geometry, click on import. The 3D wing geometry is imported. Next step is to create domain. We will use enclosure function to create domain or virtual wind tunnel. For that, right click on wing, add geometry operation. Here we have enclosure function. Click. Here, enter the dimensions of enclosure or domain. And click on start. Here, domain is generated for our geometry. Hide the domain, right click, hide section. Next, select active box selection. Select the wing geometry. In topological entity set, click on the plus icon. Create a new set. Name it. Right click. Click on show all. Pre-processing step in analysis is completed. The second step is solver execution step. For that, go to simulations, click on the plus icon in simulations, select incompressible and click on create simulation. Under incompressible, the turbulence model will be k omega SST and time dependence is steady state. Save it. Next, assign material. To assign material, click on the plus icon in material. The material will be air. Select air and apply. I'll give kinematic viscosity as 1.5. 1.5 meters square per second and density as 1.19 kg per meter cube. Save it. Next, initial conditions, I'll keep the same values. Next, we'll be assigning the boundary conditions. To assign boundary conditions, click on the plus icon. First, go for velocity inlet. In velocity inlet, you need to enter the inlet velocity and select the inlet phase. For the velocity inlet, I'll give the inlet velocity as 40 meter per second and the inlet phase. Let's select the inlet phase. So this is the leading edge of the wing and the trailing edge is here. So the air moves from leading edge to the trailing edge. So the inlet for the wing geometry will be this phase. Select it and save. Next, follow the same procedure. Select pressure outlet. In the pressure outlet, you need to enter the gauge pressure and select the outlet phase. Here gauge pressure, I'll enter 9.776 e⁴ Pascal and the outlet phase will be this and save it. Next, we'll apply the wall boundary conditions. In velocity, select moving wall. The wall along which the velocity magnitude is specified, that is defined as moving wall. Enter the velocity as 40 meter per second and select the moving wall of your domain. So the moving wall will be this. Select the moving wall for your domain. Select, rename it as moving wall. And save it. Next, follow the same procedure. Apply wall boundary conditions. Select slip wall. The free surfaces of the domain at which the velocity is 0 is defined as slip wall. Select the free surfaces of your domain. So these are the three surfaces or the slip walls. Rename it and save it. Now we are done with assigning the boundary conditions to the wing geometry. In advanced concepts, in numerics, I'll keep the same default values, save it. In simulation control, I'll keep the same default values, save it. Next, assign result control. In forces and movement, click on the plus icon, add forces and movement. Here, enter the CG value of your geometry. In the scene tree, here under topological entity set, select wing as assigned phase. And save it. Next, follow the same procedure. Add forces and movement coefficient. Enter the same CG value. Lift is along Y. Enter 1. The remaining will remain 0, 0. Drag is along X. So dx will be 1 and the remaining dy and dz will remain 0. Pitch is along Z. Remaining xy will remain 0, 0. Enter the free stream velocity that we have entered at the inlet as 40 meter per second. Enter the reference length of your geometry and the area of your geometry and select the wing under topological entity set and save it. Here we have done with the result control. Next is to generate mesh. To generate mesh, click on mesh. Keep the same default values. To generate mesh, click on generate. Mesh generation step is completed. You can see the mesh generated on the domain. Hide the domain. You can also view the mesh generated on the wing surface. Right click, show all. After the mesh generation step is completed, the final step in solver execution is to run simulation, one needs to ensure that in the navigation tree, each node has a green tick. So here we have green tick on each node. So let's move to simulation run. To run simulation, click on the plus icon in simulation run. The simulation duration is 33 to 49 minutes. Click on start. The simulation step is finished. The solver execution step completes here. The next step is post-processing step. Next, we shall move to the post-processing step. To analyze the values of lift, drag, lift coefficient and drag coefficient, go to force plot, click on forces and movements. Here, the pressure force X is the drag force and pressure force Y is the lift force. Disable the other options. First, we will view the lift force. It is 182.01 Newton. The drag force, that is pressure force X, is 14.29 Newton. Next, to view the lift coefficient and drag coefficient values, go to force coefficient plot, forces and movement coefficients. Disable the other options. First, we will see the lift coefficient value. It's 0.189. Drag coefficient value is 0.0163. In this way, you can view or analyze the lift and drag forces, lift coefficient and drag coefficient values for your geometry. Next, we will view the velocity and pressure counter plot. For that, click on Run. Click on Post Process Results. In parts color, I'll select pressure. Hide the domain section. This is the pressure counter plot for the wing geometry. Next, add cutting plane. Select translucent surfaces with wireframe. Orientation is Z, and here I'll keep velocity magnitude itself. Disable parts color. This is the velocity magnitude counter plot for the wing geometry. Next, to view the streamlines flowing over the surface of the wing, add particle trace. Disable cutting plane. Right click, show all. Click. You can increase the vertical and horizontal feeds. I'll do it 50, 50. You can also change the spacing and size of the seats. So I'll change the size. I'll change the size of the seats. Hide the domain. Here you can see the streamlines flowing over the surface of the wing. In parts color, select solid color. You can also animate the streamlines. Let's animate the streamlines. Add animation. Select particle trace. Increase the steps and the animation speed. Play. This completes the post-processing step. The, this completes the analysis of aircraft wing.